A suffix is a part of a word that is added onto the end of a root word and cannot stand alone. So many times in a word, you have a prefix, a root, and a suffix. And so the prefix, the root word, and the suffix all combine to make one word. Now sometimes you only have a root word, sometimes you just have a prefix and a root word, and sometimes you just have a root word and a suffix, and sometimes you really just have a prefix and a suffix. But you're never just going to find a prefix, and you're never just going to find a suffix. It has to be paired with something else. Now a suffix has a meaning of its own, and so it changes or enhances the meaning of the root word that is added to it, and so it forms a new word with a little bit of a different meaning. So we have the word happy. Now we also have a suffix, which is N-E-S-S. Now this line right here means that it's a suffix. If the line was after the word, it would mean that it's a prefix. But right here, this means it's a suffix, meaning the root word comes before it. So now if we combine happy and ness, we get the word happiness. And so we know what the root word means. We know what it means to be happy or joyful. But ness right here means the state of. So the suffix right here changes the meaning of happy to mean the state of being happy. So you can say that person is experiencing happiness. You wouldn't say they're experiencing happy, but you would say they're experiencing happiness. Now, think about the word geometric. You may not even be familiar with this word, but you're probably familiar with some of the parts of it. So we have geo, which is the prefix right here, and so that means earth. So I'm just going to write that right here. Geo means earth. And then we have this right here, M-E-T-R-I, which means the measure of. It's kind of similar to the word meter. And then we have the suffix IC, which means having to do with. So we can come up with a definition here that means having to do with measuring the earth, because we have these definitions of the parts of the word, so we combine it into one approximate definition. Now, if you were to look up this word in the dictionary, you would find that the dictionary definition is of or relating to the branch of mathematics that has to do with measuring points, lines, and angles. So by using the definitions of each section of the word, we weren't necessarily able to define exactly the definition of this, but we were able to get a general idea. Now, think about the word ophthalmology. So with this word right here, we have this first part of it, which comes from the word ophthalmos, which means eye. And then we have the suffix right here, which is ology, which you've probably heard of a lot. Zoology, ecology, geology. And ology means the study of. So again, we can come up with an approximate definition. So this must mean the study of the eye. And so an ophthalmologist is someone who studies the eye. And so it's a doctor who deals with eye problems and does eye surgeries. So if you just looked at ophthalmology and thought that's the study of the eye, you're not getting an exact definition of what ophthalmology is, but you're getting an idea that it's the study of the eye and the problems with it. And so there's definitely going to be a more specific definition of it, but you're able to get a general idea of what it's talking about. Now, a couple of the suffixes we looked at here were ness, ick, and ology. And there are many more suffixes. And so if you're able to learn the meaning of some of the suffixes, then you can oftentimes just look at a word and figure out what it means. Another thing you can do, say, for example, like I said earlier, say you saw the word zoology. And so you don't necessarily know what this means. Say you don't know that ology means the study of. But you have heard of the word geology, and you know that means the study of the earth or of rocks. And so you can look at this right here and think, okay, ology must mean the study of, and I've heard of the word zoo, that's a place with a lot of animals, so zoology must mean the study of animals. So think about words that are like this word, think about words that have the same suffix, and think about the definitions of that word, and then that way you can figure out the definition of the word in question. So again, a suffix is a part of a word that is added onto the end of a root word and cannot stand alone.
Factors. Factors are numbers that are multiplied together to obtain a product. For instance, in 2 times 3 equals 6, 2 and 3 are the factors. Common factor, a number that divides exactly into 2 or more other numbers. For example, the factors of 12 are 1 times 12, 2 times 6, and 3 times 4. So the factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 15 are 1 times 15 and 3 times 5. So the factors of 15 are 1, 3, 5, and 15. The common factors are 1 and 3. Those are the factors they have in common. Prime number. Prime numbers have 2 distinct, which means different, factors. 1 and itself. The very first prime number is 2, because the only factors of 2 are 1 and 2. 1 times 2 is 2. Some people think that 1 would be the first prime number, but 1 only has one factor, 1. 1 times 1 is 1. So 1 is commonly thought of as neither prime nor composite. A composite number being a number that has more than 2 factors. So 2 would be the first prime number, then 3, because 3 has only 2 factors. 1 times 3 is 3. 4 would be composite, since 1 times 4 is 4, and also 2 times 2 is 4. 5 would be prime. Its only factors are 1 and 5. 6 would be composite. 1 times 6 is 6, and 2 times 3 is 6. 7 would be prime, since its only factors are 1 and 7. 8 would be composite. 1 times 8 is 8, 2 times 4 is 8. 9 would also be composite. 1 times 9 is 9, 3 times 3 is 9. 10 would also be composite. 1 times 10 is 10, 2 times 5 is 10. 11 would be prime. 1 times 11 is 11, and so on and so forth. There are an infinite number of primes. A prime factor is a factor that's prime. So in our example above, in 12 and 15, the prime factor of 12 would be 2 and 3, and the prime factors of 15 would be 3 and 5. You can also do prime factorization. The prime factorization of a number, for instance, the prime factorization of 12 would be 2 times 2 times 3. That's where you write the product of a number only using primes. And the prime factorization of 15 would be 3 times 5. Unlike just writing the factors of a number. With prime factorization, you use only prime numbers as factors to multiply to get the result of the product you are seeking. Fractions. A fraction is a number that is expressed as one integer written above another integer with a dividing line between them, like x divided by y. So for example, 3/4. In this fraction, 3/4, the top number is called the numerator, and the bottom number is called the denominator. The numerator is the part that's being considered, while the denominator is the whole. So in this fraction, 3/4, we could take a pie shape and cut it into 4 pieces. That's our whole. And the part that's being considered is 3/4. So 1, 2, 3. So now you can see how much of our pie we're talking about, 3/4. We can manipulate fractions, and we do this by multiplying or dividing both the numerator and the denominator by the same number, not by adding and subtracting. We manipulate fractions to do many things. One thing is to compare them. If we were to compare 3/4 and 2/3, we would first need to find what's called a common denominator. Because in order to compare them, I need them to have the same denominator. So I can tell which one's bigger or if they're equal. So we'll take 3/4 and 2/3, and we're going to find a common denominator. When you do that, you want to look for multiples of the denominators. And the least common multiple will be the least common denominator. So the multiples of 4 and 3, 4 is 4, 8, 12, 16, etc. 3 is 3, 6, 9, 12, 15, 18, etc. So the least common multiple between 4 and 3 is 12. So that means I want to change this fraction to something over 12. Same with my other fraction. What I'm doing is creating an equivalent fraction. 3/4 is equal to something over 12. So I'm going to multiply my numerator and my denominator both by 3 to achieve that denominator of 12. So 3 times 3 is 9. And so our fraction is 9/12. And then for 2/3, we'll do a similar thing. We want to change our denominator from 3 to 12. So we multiply 3 times 4 to get 12. And we must do the same to our numerator. 2 times 4 is 8. So now we can easily see which fraction is larger. 3/4 is equivalent to or equal to 9/12. And 2/3 is equal to 8/12. Well, 9 out of 12 is definitely more than 8 out of 12. So we could say that this fraction 3/4 is bigger than this fraction 2/3 if we were to compare them. So let's talk a little bit more about equivalent fractions. All of these fractions are equivalent fractions because they all represent the same value. 2/10, 3/15, 4/20, 5/25. And we could see that they represent the same value more easily by simplifying our fractions. So we said we can manipulate fractions by multiplying the numerator and denominator by the same value, or we can manipulate them by dividing the numerator and denominator by the same value. So if we wanted to simplify this fraction 2/10, we would just divide the numerator and the denominator by the same value. Both 2 and 10 are divisible by 2. So we divide our numerator by 2 and our denominator by 2. 2 divided by 2 is 1. 10 divided by 2 is 5. We do the same thing to our next fraction. 3 and 15 are both divisible by 3. So we divide our numerator by 3 and our denominator by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. 4/20. Our numerator and denominator are both divisible by 4. So divide by 4, divide by 4. 4 divided by 4 is 1. And 20 divided by 4 is 5. Finally, 5/25. Numerator and denominator are both divisible by 5. 5 divided by 5 is 1. And 25 divided by 5 is 5. So as you can see, all 4 of these fractions are equal to 1/5. 1/5 is the simplest form of these fractions, and they are all equivalent fractions since they all have the same value, 1/5. Laws of exponents. We're going to look at 7 different laws. The first is that any number raised to the first power is just itself. If you'll remember what an exponent is, it tells you how many times to multiply the base number times itself. So if you're multiplying the base number times itself, well, just one time, then that's just that number. Like 2 to the first power would just be 2. Or -3 to the first power would just be -3. The second rule says that 1 raised to any power is 1. Because all you're doing is multiplying it 1 times itself, and no matter how many times you multiply 1 times itself, it'll always be 1. So for instance, like 1 to the third power, that means 1 times itself 3 times. 1 times 1 is 1 times 1 is 1. So it doesn't matter how many times you multiply 1 times itself, you'll always get 1. The third law says that any number raised to the 0 power is 1. This is one of my personal favorites. I think it's pretty cool. Like 8 raised to the 0 power. It's just 1. Or -10 raised to the 0 power. Again, just 1. Or even say like a half raised to the 0 power. Still 1. Any number raised to the 0 power is always 1. The fourth law is when you're multiplying with the same bases. So notice A and A, our bases are the same, but we have different exponents. When you multiply numbers with the same bases, you add the exponents. Let's look at why. So say we were doing 2 cubed times 2 to the 4th. Well, what that really means is 2 cubed is 2 times itself 3 times, so 1, 2, 3 times, times 2 times itself 4 times, so 1, 2, 3, 4 times. So we've multiplied 2 times itself a total of 7 times. So instead of going through all of this, we can just use that rule that when we multiply numbers with the same bases, we simply add the exponents. And then you could simplify from there. The fifth rule is pretty similar to the fourth rule, except we're dividing numbers with the same bases. So instead of adding our exponents, we subtract our exponents. For example, if we were doing 2 to the 5th divided by 2 cubed, what we're really doing is 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2. So that's 2 to the 5th, 2 times itself 5 times, divided by 2 times itself 3 times. Well, we can simplify by canceling. 2 divided by 2 is 1, 2 divided by 2 is 1, and 2 divided by 2 is 1. So what we're left with then is simply 2 squared, or 4. So instead of doing this, we can use our rule that when we're dividing numbers with the same bases, we simply subtract the exponents. And that saves us a little bit of time. 2 to the 5th divided by 2 cubed, 5 minus 3 is 2, so it's 2 squared, which is 4. It also works if your denominator, the exponent on your denominator, is larger. Let's look at one of those. So that'd be like 2 squared divided by 2 cubed. So you still subtract your exponents, so it's 2 squared minus 3, which is 2 to the negative 1. And then you would simplify that by bringing this to your denominator, 1/2. The sixth rule says that when you raise a power to a power, like a to the n raised to the m, you multiply your exponents. So for instance, with 3 squared cubed, what that really means is 3 squared times itself 3 times. So that's 3 squared times 3 squared times 3 squared. 3 squared times itself 3 times. 3 squared times 3 squared times 3 squared is 3 to the 6th. So all you have to do is multiply your exponents. 2 times 3 is 6, 3 to the 6th. The seventh rule says that when you have operations inside parentheses that are raised to an exponent, then each term inside those parentheses is raised to that exponent. So for instance, like 2 times 3 squared. That is 2 squared times 3 squared. And again, you could simplify from there. Left off my n there, that's important. Now on this next one, same thing, just with division. So a divided by b, that quantity raised to the n, would be a to the n divided by b to the n. So everything in the parentheses is raised to the n power. So it'd be like doing 4 divided by 3 cubed. So that'd be 4 to the 3rd divided by 3 to the 3rd. And then again, you could simplify. And those are our laws of exponents. Decimals. Decimals use place value to represent an amount. To read a decimal, like we have here, first read the number to the left as a whole number, followed by and, then read the number to the right of the decimal, followed by the last place value. So this number would be read as 641 and 5,129 10,000ths. This number could also be represented as a mixed number. 641 and 5,129 10,000ths. Let's look at another decimal. 5 and 8,139 10,000ths. we could write this number as an improper fraction by taking the 5 plus, this would be 8/10 since it's in the tenths place, plus 1/100 plus 3/1000 plus 9/10,000, which would give us 58,139 10,000ths. So we've seen a decimal in decimal form. We've seen it represented as a mixed number and also as an improper fraction. Exponents. Exponents or powers represent the number of times a base number is multiplied by itself. For example, 3 to the 4th power is 3 multiplied by itself 4 times because of the exponent 4, which is 3 times 3 is 9, times 3 is 27, times 3 is 81. Let's look at this set of numbers here. 2 to the 4th is 2 times itself 4 times. 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 cubed, or 2 to the 3rd power, is 2 times itself 3 times. 2 times 2 is 4, times 2 is 8. 2 squared is 2 times itself 2 times. 2 times 2 is 4. 2 to the 1st power is just 2 times itself 1 time, or just 2. Now 2 to the 0. That's one that seems tricky at first. So let's look at this pattern to see if we can figure out what it would be. If you look at this set of numbers here, with each number, my exponent has been reduced 1. And it continues to be reduced by 1. And if we look at the pattern of the result, 16, 8, 4, 2, you can see that the pattern is 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So if we continue with our pattern, if we continue dividing by 2, then the next number in our sequence, 2 divided by 2, would be 1. So 2 to the 0 power is 1. Continuing with our pattern, dividing by 2, 1 divided by 2 is the fraction 1 divided by 2. So 2 to the negative 1st power is 1/2. Continuing with our fraction, so again dividing by 2 again, 1/2 divided by 2 is 1/4. So 2 to the negative 2 power is 1/4. What you're doing with these negative exponents is that you're taking your base number to the negative exponent and you're doing the reciprocal of that. So 2 to the negative 1 is really 1 over 2 to the positive 1st power, which is 1/2. 2 to the 1st power is 2. Same thing with 2 to the negative 2 power. So again, we're going to find the reciprocal of that. 1 over 2 to the 2nd power. 2 squared is 4. So we have 1/4, which is where that number came from. Regardless of the base, it's true that a number raised to the 0 power equals 1. It'll always be 1. 5 to the 0 power is 1. 10 to the 0 power is 1. Any number to the 0 power is always 1. And a number raised to a negative power is the reciprocal or the multiplicative inverse of that number raised to its positive counterpart, like we did here. So let me show you one more example using a different number. 5 to the negative 4th power would be 1 over 5 to the 4th power. So finding that multiplicative inverse is how we get rid of that negative on our exponent, which is 1 divided by 625. Greatest common factor. The greatest common factor, or GCF, of two numbers is the largest value that divides into each of the numbers. Let's take, for instance, 18 and 30. You can find the GCF of two numbers by finding the prime factorization of your numbers and then finding what they have in common. So the prime factorization of 18 is even, so it's divisible by 2. So 2 times 9 would be 18. 9 is not prime though, so we need to break 9 down. And the factors of 9 are 3 times 3. So the prime factorization of 18 would be 2 times 3 times 3. 3 times 3 is 9, times 2 is 18. I always like to check after I've factored to make sure I've got it. The prime factorization of 30. 30 is divisible by 2 also, since it's even. So 2 times 15 would be 30, but 15 is not prime. So we have to break it down into its prime factors. And 15's prime factors are 3 times 5. So the prime factorization of 30 is 2 times 3 times 5. 2 times 3 is 6, and 6 times 5 is 30. Now again, to find the GCF, we're going to look for what they have in common. 18 and 30 have 2 and 3 in common as prime factors. So we take those factors they have in common and multiply them. 2 times 3 is 6. So the GCF of 18 and 30 is 6. 6 is the largest factor that these numbers have in common. Least common multiple. The least common multiple, or LCM, of two numbers is the smallest value divisible by both the numbers, or it's the smallest number that both of your numbers divide into evenly. The LCM can be found by finding the GCF, or greatest common factors, and the remaining factors. The LCM is the product of the GCF and those remaining factors. For example, if we wanted to find the LCM of 18 and 30, we would first need to factor them. 18 is 2 times 9. Since 9 is not prime, we would factor 9 to 3 times 3. 30 is also even, so we'll start with 2. 30 is 2 times 15. 15 is not prime, so we factor 15. 15 is 3 times 5. The GCF, or greatest common factor, is 2 times 3, or 6. So our least common multiple is the product of our GCF, 6, and the remaining factors. The remaining factors are 3 and 5. So 6 times 3 times 5. 6 times 5 is 30. 30 times 3 is 90. So the smallest number that 18 and 30 will both divide into evenly is 90. Order of operations. Before simplifying expressions, it is important to know which operations to perform first if more than one operation is present in the expression. Please excuse my dear Aunt Sally, or PEMDAS, is often used for remembering the order of operations. P is for parentheses. Anything in parentheses should be done first. This one's a little misleading though, because it's not just parentheses that should be done first, it's all grouping symbols. Brackets, absolute value, anything that groups numbers together. Followed by exponents, and then their inverses, roots, should be done next. Following that is multiplication and division. And this is special because multiplication and division, it's not that one needs to be done before the other. These are just worked from left to right. So in your expression, when you're looking from left to right, you'll do all your multiplication before you do your division. Finally, addition and subtraction work the same way as multiplication and division. So these will also be done from left to right, but these will be the last things done when simplifying an expression. Let's put PEMDAS to work. We're going to simplify this expression. So according to PEMDAS, we need to start with our parentheses or our grouping symbols. 3 plus 9 then is where we need to start. That's the only thing we're going to simplify, so everything else stays the same. 2 plus 5 minus 3 plus 9 is 12 divided by 2 squared. We're done with our parentheses or grouping symbols, so next up is exponents. And we have an exponent right here at the end, so 2 squared will be the next thing we simplify. 2 plus 5 minus 12 divided by 2 squared means 2 times itself 2 times, which is 4. Then we have our multiplication and division from left to right. So as I look from left to right, all I have is this one division operation to perform. So that'll be the next thing we do. 2 plus 5 minus 12 divided by 4 is 3. Finally, we get to our addition and subtraction. Again, these are worked from left to right. So 2 plus 5 is 7. Bring down our minus 3. And 7 minus 3 is 4. So this expression, simplified, would give you 4. Now let's see what happens if we ignore the order of operations and just work from left to right. If we were just working from left to right, we would start with 2 plus 5, which would give us 7, minus 3 plus 9 divided by 2 squared. Then we would do our 3 plus 9, so we'd have 7 minus 12 divided by 2 squared. 7 minus 12 would give us negative 5, since we can add the inverse. 7 plus negative 12, negative 5, divided by 2 squared. Negative 5 divided by 4 is negative 5/4. So as you can see, if we ignore the order of operations, we get a completely different answer, which is why it's very important to make sure you're always going in the correct order whenever you solve or simplify an expression. Percentages. Percentages are values that are used to compare numbers to 100. All percentages equal the number divided by 100. For example, 35% means 35 out of 100. So you could express it as 35 out of 100, which could then be simplified to 7/20. You could also write 35 out of 100 as a decimal 35 hundredths. So percentages again, are just that number out of 100. Let's take 85%. 85% means 85 out of 100, which can also be simplified to 17/20ths. And 85 hundredths can be written as a decimal, 85 hundredths.
In math, we have rational numbers and we have irrational numbers. So we're going to be taking a look at rational numbers, which have 4 different categories, and those are integers, percents, fractions, and decimals. So we're going to define each of these. Even if you're already somewhat familiar with them, we're going to go ahead and define them and give some examples. So starting out with integers. Integer is a positive or negative whole number or 0. So 9 would be a whole number. It would be an integer because it's a positive whole number. -6 is an integer because it's a negative whole number. Then of course 0 is an integer because we said it was. And so now we move on to percents, which is kind of a more complicated way to say percent is a part per 100. So an example of a percent is 20%, which we could also write as 20 parts per 100. But the important thing here is just you know what a percent is, like 20%. Then fractions, which is a proportion. So an example would be 20 divided by 10 or 2 divided by 4. Then of course we have decimals, so this is where we have an integer, maybe 1, maybe 89, maybe 0. And then we have a decimal place, and then we have numbers after the decimal, like 20.53. So we have our integer, we have a decimal, and then we have numbers after the decimal. So integers, percents, fractions, and decimals are all rational numbers, usually. There are some rules. So in order to be a rational number, to summarize, it either has to be an integer, like we talked about. If it's a number like 9, -6, 0, it's always going to be a rational number. It gets more complicated when we come to fractions and decimals. If it's a fraction, it has to be an integer divided by an integer. And this integer cannot equal 0. So it's an integer divided by an integer. So 7 divided by 4 cuts it. That works. Now, decimals are a little bit more complicated because it either has to be a terminating decimal or a repeating decimal. So an example of a terminating decimal would be something like 2 divided by 4. From that you get 0.5. It ends right there at the 5. For a repeating decimal, you do 1 divided by 3 and you get 0.3333. It goes on forever. But notice we're getting the same number every time. So really you could erase all of these 3's and just put a line over the 3 showing it's a repeating decimal. What you don't want is a decimal like pi, where you have 3.1415926, 5359. It just keeps going on and on. So there's no ending to it, so it's not a terminating decimal, and there's no pattern to it, so it's not a repeating decimal. That's what an irrational number is, one that just keeps going like this. These numbers, they have basically a stopping point. And so that's what we're looking for. And so the reason I say that a fraction has to be an integer over an integer is because when you divide an integer by an integer, you get a clean number. You get a decimal that's repeating or terminating. When you start dividing a decimal or a fraction by a number, or a fraction by another fraction, that's when you're going to start getting messy. So really, if you're wondering whether a fraction is a rational number, what you can do is go ahead and divide it out and then look at the decimal and decide whether it's terminating, repeating, or non-ending. And that's how you can determine if it was a rational number.
Ratio, proportion, and fraction are 3 terms that mean the same thing, a part of a whole. Now let's say, for example, we're baking cookies. And we have a ratio of 2 cups of sugar to 24 cookies. So for every 24 cookies, we know we need 2 cups of sugar. That is the ratio, 2 to 24. Now, let's say that we know what our ratio is, and we know how many cookies we like to bake. And in this instance, it's not 24, but 30. How many cups will we need? How many? That is the unknown quantity. How many? We can use the known quantities in the ratio, 2 cups of sugar, 24 cookies, and the known quantity of cookies to determine the unknown quantity of sugar that we need for 30 cookies. Now, whatever this ratio comes out to be, it will be equal to 2 to 24, or 2 cups of sugar to 24 cookies. So because of that, we're going to use a process called cross multiplication. So first we'll multiply 2 times 30, which gives us 60. And then we're going to multiply 24 times C. C is the unknown variable. So 24 times C is equal to 24C. Once we've done that, we're going to use another process called isolation. We're going to isolate the variable and its coefficient, which is 24, by using the coefficient 24. We're going to isolate 24C. And because we have an equal sign here, anything we do to one side, we have to do exactly the same to the other side. So we divided 24C by the coefficient 24, and we will divide 60 by 24 as well. So what does that leave us with? Well, the 24 in the 24C in the numerator and the 24 in the denominator will cancel themselves out, and that leaves you with C, 60 over 24. We need to simplify that. So we come over here and we divide 24 into 60. 24 goes into 60 2 times. 2 times 24 is 48. 48 minus 60 leaves us with 12. Now, of course, this is going to be a mixed fraction, so we bring the 24 down here to be the denominator. That's 2 and 12 24ths. We simplify this number because it can be simplified, and it comes out to 1/2. So our answer is 2 1/2 cups of sugar will be needed for 30 cookies.
Multiples. You can think of multiples as like counting by that number. So for instance, the multiples of 2 would be 2, 4, 6, 8, 10, etc. The multiples of 3 would be 3, 6, 9, 12, 15, 18, etc. The multiples of 4 would be 4, 8, 12, 16, 20, and so on. Sometimes you're asked to find the LCM of 2 or more numbers. The LCM is the least common multiple. Least meaning the smallest, common meaning the same, and multiple. So if we wanted to find the LCM of, let's say, 2 and 3, the least common multiple of 2 and 3, so the smallest number that 2 and 3 have in common, would be 6. So that's the LCM of 2 and 3. The LCM of, say, 3 and 4, the very smallest number that they have in common would be 12. And you can find the least common multiple of bigger numbers, like say the least common multiple of 12 and 15. So 12 would be 12, 24, 36, 48, 60, 72, etc. While 15 would be 15, 30, 45, 60. Oh, so if we were finding the LCM of 12 and 15, the smallest number they have in common is 60. So the least common multiple is 60. Numbers and their classifications. First we have integers. Integers are the set of positive and negative numbers, including 0, which is neither positive nor negative. But integers do not include numbers like fractions or decimals. That means no mixed numbers either. So integers would only be numbers like negative 100 or positive 7 or negative 15 or positive 2. Just no fractions, no decimals, but we can have positive and negative numbers, and it also includes 0. Next we have even numbers. An even number is any integer. So remember, by saying it's an integer, we're already not including fractions and decimals. So it's any integer, no fractions or decimals, that can be divided by 2 without leaving a remainder, which means we can divide it evenly. So an example of an even number would be 2, 4, 6, 8, 10, 12, 14, 16, etc., etc., etc. We could go on forever naming even numbers. Next we have odd numbers. An odd number is, again, any integer, so no fractions or decimals, only positive and negative numbers including 0, that cannot be divided evenly by 2. So the exact opposite of an even number. Even numbers can be divided by 2 evenly, and odd numbers cannot be divided evenly by 2. And so an example of those numbers would be numbers like 3, 5, 7, 9, 11, 13, 15, 17, 19, etc., etc., etc. A decimal number is a number that uses a decimal point to show the part of the number that is less than 1. For example, in the number 1 and 256 thousandths, we use this decimal point to show this part that is less than 1, rather than using a fraction. And so then we get to decimal point. A decimal point is a symbol used to separate the ones place from the tenths place, like we did in this number right above us. This decimal point separates our ones place from our tenths place. So it shows you which part of the number is 1 or greater and which part of the number is less than 1. Finally, decimal place. That's the position of a number to the right of the decimal point. So in this number, 0 and 123 thousandths, the 1 is in the first position to the right of the decimal, and so that's the tenths place. The 2 is in the second place to the right of the decimal, that's the hundredths place. And the 3 is in the third position to the right of the decimal. That's the thousandths place. And it continues on like that. Tenths, hundredths, thousandths. Next would be 10,000ths, 100,000ths, and so on and so forth. Notice that they all end in a THS. So it's not 10,000, it's 10,000ths because it's decimals. So what our whole system is based on is the base 10 system. We have 10 different digits to work with, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we can arrange those numbers in lots of different ways that mean lots of different things. But of course there are other systems besides the base 10 system, like the binary system. And that's what computers use. And the binary system, that prefix bi means 2. So in the binary system, they only use 2 numbers, 0 and 1. And they put those numbers together to mean different things as well. It's thought that maybe we use the base 10 system because we have 10 fingers and maybe 10 toes, so it was just easier to come up with something like the base 10 system. But these are our numbers and what these different words mean. Parentheses. Parentheses are used to designate which operations, which is addition, subtraction, multiplication, division, should be done first when there are multiple, so more than one, operations. For example, 4 minus the quantity 2 plus 1. Since 2 plus 1 is inside the parentheses, we must perform that operation first. We must add 2 plus 1 first. So 4 minus 3, which yields 1. If we had not added 2 plus 1 first, then 4 minus 2 would be 2, plus 1 would give us 3. So there would be a different answer. So that's why we need to know that parentheses mean that we do that operation first.
ACT, English sentence structure. The sentence is the basic unit of communication in English. Parts of speech identify the words which make up a sentence. So some examples of parts of speech are nouns, verbs, adjectives, adverbs, pronouns, articles, interjections, prepositions, and conjunctions. So one group of words that we have is nouns, verbs, adjectives, adverbs, and pronouns. Those words perform essential functions within a sentence. In addition to performing essential functions, they also provide content. So they give the sentence its content, which makes sense because you have the nouns and the pronouns, which act as subjects, and then you have your verbs, which obviously act as verbs in the sentence. In every sentence, you need a subject and a verb, which gives you the topic of the sentence, and then the verb tells more about that topic. And so you can understand how these parts of speech right here perform essential functions and provide content. And then we also have another group of words, or another group of parts of speech called the prepositions and conjunctions. And so those words connect sentences. And they connect one part to another. And when I talk about one part, I'm talking about one part of a sentence. So these prepositions and conjunctions can connect sentences to each other, and then within a sentence, they can connect one part, either one idea or one action, to another idea or action. Now, some words function only as one part of speech. However, many words can function as 2 or more parts of speech. Just depending on the context of the sentence, a word will be either one part of speech or another part of speech. And so that's a look at the different parts of speech in a sentence.
In this video, we want to go over prefixes. Prefixes are short little sections of words that come before the root of a word and help you understand what the word means. They add an extra nuance to the word. And why prefixes and suffixes, for that matter, are important, prefixes coming before the root of the word, suffixes, short little endings after the word, is that if you know your basic prefixes and suffixes, they help you determine the meaning of a word. And they're important clues, especially if you're taking a standardized test where they say we want you to find the word with the opposite meaning. Sometimes just knowing the prefix can give you enough of a clue, even if you don't know what the root means, to find the opposite. We've got a few examples on the board and we want to go through those briefly just to show you the importance of prefixes, how they can help you in your test-taking strategies, and how they can help you understand the meanings of words. So prefixes give clues as to a word's meaning. Knowing them can help you find the word with the opposite meaning on a test. So words like prefixes like pre. Here we think pre-operative, pre-op. That means before the operation. Or prescient. Pre meaning before, and scient from the word science, which means knowledge. So to know ahead of time. So prescient is to know ahead of time. Pre-game show, the part that comes before the game. So pre means before. The opposite of pre is post. Post-operative care, the care that happens after the operation. Post-game show, the show that happens after the game. So pre is before, post is after. If you realize this opposites, then if you see a word that's got a pre prefix on it, then you look for a word with a post prefix on it if the test is asking you to find the opposite. Another thing would be pro and d. So pro means for, as in pro-life. Someone who is pro-life is for life. DE is the negation, so deconstruction. To deconstruct is the opposite of, or the negation of construction. Construction to build up, deconstruct to destroy. So pro meaning for, D is usually a negation, pre before, post after. Knowing your prefixes can be critical, especially if you're not sure of the whole word. You can say, well, let me break this word up into its prefix, its root, and its suffix, and see if I can't decode just from that minimal information the proper answer on the other side. Now, obviously, when you're taking a test, if you know the right answer, you always go with the right answer. But if you're struggling, if you're not sure, this is a strategy you can use. You can look at the word, break it down, and say, here's the prefix, and I know it means this, and I'm being asked to find the opposite. What's the opposite of this prefix? Then I've got my answer more than likely. Caution though, caution. Con and pro are opposites, but congress is not the opposite of progress, although some people might disagree. That's more of a joke in terms of Congress being the opposite of progress, but con and pro are opposites, but you have to know and be careful sometimes. Anyway, that's been just a basic introduction and overview of the importance of prefixes as a test-taking strategy of knowing what they mean to help you determine the meaning of a word, and also to assist you if you're being asked to look for the opposite. If you know what the prefix means and you know what the opposite of that prefix is, it makes it a snap to find the right answer. If you'd like to learn more about this or related matters, underneath this video you'll see a link. If you'll click on that link, it'll take you to the website that has that information. While you're on that website, you'll also find a link to an ebook that's ready for immediate download.
Water is essential to life as we know it, and it is one of the main, or the main constituent of many living things. And so there's several interesting properties of water I want to take a look at. So first is its high polarity. It has negative and positive ends. And this is due to the fact that water is made up of 2 hydrogen atoms and only 1 oxygen atom. And also hydrogen bonding. Water molecules engage in hydrogen bonds with other water molecules. Water also is cohesive. And so cohesiveness means it's attracted to itself. You may have noticed this if you ever filled a cup of water up a little bit too high above the rim of the glass. Well, the water didn't immediately spill over because of cohesiveness. The water molecules were attracted to the other water molecules, so the water didn't necessarily spill out because the attraction was stronger than the force of gravity trying to pull it out. Then we also have adhesiveness, which means water molecules are attracted to other molecules. Water has a high specific heat, which means it resists the breaking of its hydrogen bonds and resists heat and motion. So specific heat means that it has a large amount of heat required to raise temperature by a specific amount. This also kind of goes along with high latent heat, which is the net heat change in change of state. So basically when water changes from one state to another, that means there was a lot of heat either absorbed or put off. And so net heat change means how much water was absorbed or exerted to do this change of state. Now, water in its solid form as ice floats in its liquid state of water. Now, this is pretty odd because many times substances are denser in their solid forms, but water is strange in that its solid state floats in its liquid state. This is because when water is frozen, it expands, and so it becomes less dense because it's taking up a larger amount of space. So that same material is spread out over a larger amount of space, which means it's less dense than the liquid water. And so when anything is less dense than water, then it's going to float in that water. So that's why ice cubes float. So that's a look at some of the interesting properties of water.
Roots. A root, such as a square root, is another way of writing a fractional exponent. This is the radical symbol, which is used to denote roots. This would be read as the nth root of a. There will be a number underneath the radical sign, and sometimes there's going to be a number right here in the upper left. If there isn't a number there, then it's simply a square root, like the square root of a. So we don't put the 2 there, it's just understood that it's there. With a 3 here, this would be read as the cube root of a, and those are our special ones that we've given names to. So after that, say you had 4, that would be the 4th root of a, 5th root, 6th root, 7th root, but square root and cube root have been given special names. So this as a fractional exponent would be a to the 1 over n, which means this would be a to the 1/2, since that little number right there is a 2, even though we don't write it. And this would be a to the 1/3 because of the little 3 there. Now the 1 comes from the exponent on the a. And since there isn't 1 there, it's understood to be 1. But say this was a squared or a cubed. Let's take this one. Say this was the cube root of a squared. Then this would be a to the 2/3. Or like this one, if we had the 4th root of a cubed, then that would be a to the 3/4. So you can go back and forth between using radicals or using exponents to denote the same thing. A perfect square is a number that has an integer, which means no fractions or decimals, for its square root. So here are the perfect squares from 1 through 100. These numbers came from squaring the numbers 1 through 10. 1 squared is 1. 2 squared is 4. 3 squared, 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100. When you say something like 10, well, I'll write it right here. 10 is the square root of 100. What you're saying is that 10 times itself is 100. So there's a quick overview over roots.
Anytime when you're taking a test, it's always good to have little things that help you narrow down the responses to choose from. Now the rule, which is inviolable, is this. If you know the right answer, always go with what you know. If you know the right answer, there's no point in playing these sorts of games and trying to narrow down the choices. You go with the right answer every time. However, as you're taking a test, there will be more than likely questions where you are not quite certain of the answer. You're not sure what you should do. This particular technique can be helpful. When you're looking at a question or a problem, that problem or question is going to provide you with some level of information. This information that is provided in the question or the problem can be called the rules. So the known information is the rule in that question or problem. So as you look at the question or problem, take the information they give you and say, okay, this is the rule. This is what I know to be certain. Then, any choices for answers beneath that question or problem that are in conflict with the rule can be immediately and quickly ruled out. You can remove them from consideration because they are in conflict with the known information or the rule. So this is the technique of the rule busters. Any answers to a problem or question that are in direct conflict with the information provided. So to give just a couple of very simple examples, the first one is John is sitting next to Bob. John is sitting next to Bob. This is the rule. Any of the answers, therefore, underneath this information, which have John and Bob not sitting next to each other or apart, can be automatically ruled out because that information, them sitting apart, is in conflict with the rule that they must be sitting next to each other. And you've already then narrowed the possibilities and choices beneath it. Another example would be Mary is not sitting next to Bob. So you can say the information given to me, the rule is that Bob and Mary, in the answer to the problem or question, cannot be sitting next to each other. Because the rule already given is they're not sitting next to each other. That's the rule. So the rule buster is if they've got them right next to each other, rule it out. It can't possibly be the answer. So this is the rule busters technique. Each problem provides some known information. This information are the rules. Any choice or choices that are in conflict with the rule, quickly rule them out, and then you're left with some fewer options to go from there, and it can help you make a more educated guess if you don't know the answer. I'll say it again. If you know the answer, you always go with what you know. But if you're not certain, this can be very helpful. If you'd like to learn more about this and related matters, underneath this video you'll find a link. If you'll click on that link, it'll take you to the website that has that information, and while you're there, you'll find a link on that website to an ebook that's ready for immediate download.
We're going to take a look at some of the properties of acids. So first off, acids have a sour taste. Now obviously not all acids are safe for consumption, but some acids that we do consume, like lemon juice and vinegar, are lowly acidic, but they're very weak acids, but they still have a very sour taste. Then acids also contain hydrogen. Now, acids will react with metals to make hydrogen gas. You can see this with metals above hydrogen in the activity series. Acids will also change the color of dyes. They will change the color of one dye in particular called litmus dye. Acids will turn blue litmus paper red, and that helps show where the acid is on the pH scale. Then acids also neutralize bases. Acids neutralize bases by combining with a base to produce a salt and water. And this type of reaction is called a neutralization reaction. And then finally, acids conduct electricity. Because acids conduct electricity, we call them electrolytes. So these are some of the properties of acids to help you better determine if a substance is an acid.
When taking your test, you may come across questions that ask you to find synonyms. Synonyms are words that have similar meaning. They don't always have the exact same meaning because there are nuances or little differences between words that may have overlap in their meanings. And so as you're looking at the word and you're looking at the options below, one of the test-taking strategies that you may find helpful is to go through the choices that you have and immediately eliminate those that you know cannot be the possible answer. And that narrows the scope down until you get closer to the actual meaning. Now obviously, if you know the answer, you always go with what you know, but if you're uncertain as to what the correct answer is, then this little strategy can be helpful. You're not looking for a perfect synonym, you're looking for something that is a close synonym, something that has a similar meaning, an overlap in meaning, even if there's some slight nuances or little differences between the words. And so I've got an example on the board. We're going to go over this just to try to illustrate this briefly. And hopefully this will help you understand the test-taking strategy of looking for the close or nearly perfect synonym if there's not one that's an exact match. So we have the word coward, and we're looking for a word with similar meaning to coward. And here are our choices then below. First one, gutless. Second one, bore. Third one, judge. And the fourth one, brave. Now, as you're looking at the word coward and you're looking at the choices, we can automatically eliminate one because it's not a synonym, it's an antonym. It's something with the exact opposite meaning. So, brave can be ruled out automatically. We know someone who is a coward is not brave. So you've got three choices left now. You think of the word coward. Pretty sure it's not the word judge. So we were absolutely certain on this one, and we're pretty sure on C. Now we're left with two answers. We've already narrowed the field. We've got a 50% chance if we just had to outright guess. But as we're thinking about the word coward, we think, well, you know, the word gutless comes pretty close to coward. It's not a perfect match, but it's closer than bore. And maybe we don't even know what a bore is. You know, someone, oh, you're such a bore. And we're not sure what that word is, but we know that gutless has some overlap and it's close. And so if we're having to guess, once again, we're not certain of the answer. I'm assuming for the case of our example here that we don't automatically know that A is the answer. But we've been able to narrow it down by eliminating the choices that we know are not correct. And when we're left with two, we've been able to narrow it further by saying, I know there's enough overlap between coward and gutless that we're going to go with A. Now, once again, this is just an example to illustrate a test-taking strategy. When you're taking your test and you come to the portion that has synonyms, if you automatically know the right answer, go with the right answer. But if you're uncertain, then basically just start looking at the answers and eliminate the ones that you know it cannot possibly be until you've narrowed it down to the ones that are possibilities, and then start looking for overlap in meaning. Because often on these tests, they're not testing your ability to find a perfect synonym. They want you to be able to realize the relationship between words and the nuances between words, the little differences, so that you can say this is close to that meaning. This is the one that has at least some overlap, even though it's not a perfect match. So we're looking for nearly perfect synonyms, not the perfect synonym when we take these tests. That's part of what the testers are trying to gauge. Do you understand the subtle differences between words, not just the one that's a perfect match as in a definition? Anyway, I hope this has been helpful for you as you take your test to think through synonyms and looking for the one that's closest or has some overlap in meaning, not the perfect match, but a close match, and the strategy of eliminating answers that you know cannot possibly be the right one. If you'd like to learn more about this and other related matters, beneath this video you'll find a link. If you'll click on it, it'll take you to a website with that information. And while you're at that website, you'll also find a link to an ebook that's ready for immediate download.